Okay everybody, what we're going to do in this last video is we're going to talk about eliminations. Specifically, how do you do eliminations that give you products that don't follow Zaitsev's rule? So if we remember correctly, the way in which Zaitsev's rule works, it tells us that when we're pulling off a proton in an elimination, the more stable product is formed by removing the protons from the position that's more substituted. So in this case, you've got this tertiary alkyl bromide. You've got two different choices. You can remove it from the secondary position here, which has 2 hydrogens, or you can remove it from this primary position here with 3 hydrogens. According to Zaitsev's rule, the more stable product, and therefore the product that's produced in the highest yield, is going to be removed from the position that is less substituted. Has more substitution. So we would remove the proton from the secondary position, forming this internal alkene here as our major product. And so if we're using a base like sodium ethoxide, so O-N-A-E-T, what we're going to wind up producing is we're going to wind up producing the Zaitzev product, which is this guy, in 79% yield, 71% yield. The product which is the anti-Zaitzev, and we're going to call this Hoffman's product, and this is going to be produced in 29% yield. And so this is exactly as we'd expect. By removing the proton from the position which is more substituted, we're going to produce the alkene with more stabilization via hyperconjugation. It's going to be more stable, and we're going to produce this in higher yield. It turns out, though, that the ability to get Zaitsev's product is related to the steric bulk of the base. So specifically, if we go ahead and look at using bases that are bulkier than something like sodium ethoxide, we can shift the selectivity of this reaction to give us the non-Zaitzev or Hoffman's product. So for example, if we shift from sodium ethoxide to sodium terbutoxide, what we're able to do is we're able essentially to turn this ratio around. So instead of giving the major product as Zaitsev's product here, what we're able to do is we're able to get this in only 28% yield, giving the major product as Hoffman's product, this terminal alkene, in 72% yield. And this is all based upon the fact that when a base is approaching a molecule like this, steric encumbrance is going to make it much easier to remove a proton from a position that's far away from other stuff than something that's right in the middle of everything. And so when we've got a base like sodium terbutoxide, so O negative, it's simply going to have an easier time pulling off this proton than working its way past this extra methyl group to pull off the proton that will give you Zaitsev's product. And you're actually able to take this to an extreme here by making a very, very, very bulky base. So for example, this is the HMDS anion, so the hexamethyl disilazide. And so what we're able to do here is we're able to take what initially was LDA and put a bunch of trimethylsilyl antlers on this sucker. And this is going to essentially behave like a moose that's trying to move through brush. It's going to get its antlers tangled on things. And so this is really going to favor the pulling off of a proton from a very sterically free position rather than the more sterically encumbered position here. And so in this case, we've moved our overall product ratio to giving us only a trace of the Zaitzev product and nigh on 99% of Hoffman's product. Okay, so this is one way in which you can favor Hoffman's product over Zaitsev's product. The other way you can do this is something called the Hoffman elimination. So let's erase the board here. Okay, so the Hoffman elimination, instead of using an alkyl halide as our leaving group, uses an alkylated amine. So for specifically, it winds up looking something like this. So you have some sort of aliphatic amine like this species here. So this will be sec-butylamine. And we're going to treat this with an excess of iodomethane, followed by treatment with basic silver oxide, followed by heat. And what this will do is this will give you the Hoffman product as the major elimination product of this reaction. So for example, with sec-butylamine, you're going to wind up getting 1-butene as your final product. And so the way in which this is going to work is that you're going to have iodomethane come in, and you're essentially going to do an SN2 reaction on this guy. And so what will happen, nitrogen will do backside attack on methyl iodide, creating your alkylated amine. We'll have a positive charge. There'll be some sort of base in solution. Might be another equivalent of amine. That's going to go ahead and remove that extra proton. And it's going to give you your alkylated species here. So in this case, it's going to be an N-methyl sec-butylamine. This is going to happen 2 more times to give us our quaternary ammonium ion. Okay. At this point, our nitrogen is actually a fairly decent leaving group. So what winds up happening is that silver oxide here is able to come through, pull off a proton, and give us Hoffman's product. And so the whole reason that silver oxide is going to prefer removing the proton from the primary position from the secondary versus the secondary position is sterics. This trimethylamine group here is absolutely gigantic. And so when trying to navigate to which proton you're going to do, sterics winds up being a really big issue for this base to come in. And in doing so, you're going to favor the production of the product that is not following Zaitsev's rule rather than the product that is. Okay. So I realize that these have been a lot of videos over the past, well, at this point probably an hour and a half. This will allow us to keep up with our lecture schedule, and so we can get all the material done by the end of the term. Thanks so much for paying attention, and I will see you on Friday.